Okay, good morning, everybody. So on Friday, we started talking about stereoisomers. How do stereoisomers differ from constitutional isomers? Okay, so constitutional, we're talking about different connections, different connectivity. The atoms are connected differently. They have a different constitution, if you will. Okay, what about stereoisomers? Okay, we can have things that are cis or trans. Different spatial arrangements, that's right. So we're talking about the same connectivity, right? But we're talking about the orientation of those atoms in space being different. So you can imagine having things connected atom by atom the same way, but having them pointing in different directions. And that's what we're talking about with stereoisomers. Okay? So stereoisomers differ from constitutional isomers in that regard. Okay? So today we're going to start talking about a nomenclature for enantiomers. What do I mean by a nomenclature? How we name them, right? Now, you all have had a little bit of this because it turns out that this semester you got to this lab before the lecture. Sometimes it's exactly the opposite. It just depends on how the weeks fall. But you already know that there's a naming convention for enantiomers, right? You don't call them enantiomer A, enantiomer B, or this enantiomer or that enantiomer, or the left-handed or the right-handed. We call them R and S, right? And so it allows us to communicate to people how the absolute stereochemistry is about a chiral carbon, for example. Okay? And then today we're going to talk about optical activity, which is a way in which we can distinguish enantiomers one from another physically. Okay? So last time we started talking a little bit about stereogenic centers, and we learned a couple of rules. One of those rules was that a molecule that has one and only one stereogenic center must be what? Chiral. Right? If a molecule contains one and only one stereogenic center, it must be chiral. What if we have two or more? Maybe, maybe not, right? What can a chiral molecule not possess? It can have some symmetry, but specifically what symmetry elements can it not possess? We can't have a mirror plane, nor can we have what? I know the weekends happen, but what can we have? What can't we have? Can't have a mirror plane, and we can't have an inversion center. Those two elements, if they are present in a molecule, by definition, it can't be chiral, because it and its mirror image would be superimposable on one another. Okay? Now, somebody said symmetry. There are symmetry elements that you can have in a chiral molecule. For example, C2 symmetry, rotation around a C2 symmetric axis. It's a little bit beyond what we're trying to talk about here, but you can have elements of symmetry. You just cannot have a mirror plane, nor can you have an inversion center. Okay? But the molecules that we have here, that we see up here, have only one stereogenic center, and so by definition it's going to be chiral, and therefore if we look at the molecule in its mirror image, they're going to be non-superimposable. So if you look at an example here we have an amino acid called leucine. For those of you who've had your biology, you should know what leucine is, right? You can see the carbon atom that has four different things attached to it. We have this alkyl chain, we have a nitrogen, we have a hydrogen, and we have a carbon to a carboxylic acid. That's four different things around that carbon, right? And it's tetrahedral, and so we're going to have an enantiomer. Here's the mirror image, right? And if we take this mirror image and try to superimpose it on the original molecule, we'll find that we can't get everything to line up, right? We can get three parts to line up, but we can get the central carbon atom and two of the groups, but you can't get the other two groups to line up, right? And remember, we built those models and we used those four color spheres, right? So one of the things that's very important for you to know on your model kit on an exam, if you had to build something like this to determine what kind of enantiomer it was, that's a lot of carbon atoms you've got to put together, right? But there's a quick way to do it, and the quick way to do it is to use those four different colored spheres. Usually we use white for hydrogen, you use blue for nitrogen, and then you could pick one of the other two colors for the carboxylic acid. So you don't have to build the entire molecule, you just have to build that chiral center or that stereogenic center, and you can figure out what kind of enantiomer you have pretty easily. Here we have 3-bromohexane, and again you can see that it has an enantiomer, and if you take them and try to superimpose them, you'll find that they are non-superimposable upon one another. So let's do a real quick concepts test. Identify the chiral centers, if there are any, in each of the following molecules: the red, the yellow, and the blue. And you can work with your partner. Take a minute. All right, let's look at the first one. Is there a chiral center in that molecule? And where is it? It's connected to the bromine. So if we look at this carbon, we see that there are 4 different things attached to it. The hydrogen is not indicated, but we know it has to be there, right? It has a bromine, a CH2, and a carbon, right? So going this way in the ring is different than going this way in the ring, and so these are 2 different substituents. So it has 4 different substituents. It is a chiral carbon atom. How about for the yellow molecule? Do we have any chiral centers? No, right? There's nothing that has 4 different substituents on it in ethylbenzene. It is an achiral molecule. How about our blue molecule here? Do we have any chiral centers? Let's go through it. Would this be a chiral carbon? No, because it contains 2 bonds to the same oxygen. Can't be, right? No, and there's not 4 different things. How about this one? It is chiral. It's got a methyl group, it's got an alkyl group, it's got this ketone, and it's got a hydrogen that's not indicated. So we would put a star there, right? How about this one? Yes, it has this alkyl group, which is different than this alkyl group. Going this direction is different than going in that direction, right? It's got an ethyl group and it's got a hydrogen. How about this one? You're shaking your head. This one? This one? Right? We've got a hydrogen attached to it. We've got an ethyl group. This going in this direction, right? You would end up going through this carbon and then this carbonyl. Going here, you would go through this carbon and then a methylene. It's different. Going this direction is different than going that direction. It's 4 different things. So yes, that's a chiral center. How about this one? Yes. This one? Nope. It's got 2 hydrogens. And how about this one? Yes. Different substituents, right? So we've got 1, 2, 3, 4 different chiral centers on this small molecule. Okay? So you would have 4 stars, so to speak, on that molecule. Okay? Now, up to this point, we've been talking about enantiomers as mirror images, and I've been talking about the one on the left or the one on the right or molecule A or molecule B. That doesn't really tell us much. We need a nomenclature in which we can identify an enantiomer and communicate that to somebody else about how those atoms are oriented in 3 dimensions. We have to start talking about the architecture, if you will, of a molecule. You know, how do you describe to somebody to build something, right? You have to give them coordinates, right? And the way that we do that in organic chemistry is we use what's called the ROS labeling system. This is approved by the International Union of Pure and Applied Chemists, okay? R and S. For those of you who are going to go into biochemistry or biology, you all will refer to this as D and L. You've learned of L amino acids and D amino acids. That's an old, archaic way of naming things, but that's how the biologists and the biochemists still do it. It's historic. D and L is actually relative stereochemistry. R and S is absolute. Okay? We know absolutely what R and S is. Okay? And so the old D and L was kind of a relative configuration naming system. Okay? We're going to use what I call the CIP rules, Cahn-Ingold-Prelog. Okay? These are rules by which you identify priorities around a carbon atom. Well, any atom, actually, but in our case, a carbon atom to determine its chirality. To designate whether or not an enantiomer is R or S, the first thing that you have to do is find the chiral center, and then you have to identify the priorities around that carbon atom. Okay? The first thing that you do is just look at the atoms that are attached, and you ask yourself which one has the highest priority. The higher the atomic number, the higher the priority for the first part of this rule. Okay? In this example, where we have bromochlorofluoromethane, that's pretty easy. Hydrogen has an atomic number of 1, right? And then bromine has the highest atomic number, then chlorine, then fluorine. We can look that up on a periodic table. We have just assigned the priorities. Okay? 4 is the lowest priority. Okay? We're playing golf here. All right? So lower number, higher priority. All right? So number 1 is the highest priority, not the lowest priority. Some texts and some websites, for those of you who go out and find other pieces of information, do it exactly the opposite. But in this class, we assign the top priority to number 1. Okay? So this would be the top first priority, second priority, third priority, and fourth priority. That's the first thing that you have to do in determining whether or not something is R or S. Okay? Now, until the 1950s, all of these configurations were relative to a natural molecule. Okay? We didn't really know where the natural molecule had specifically its elements in 3 dimensions exactly. But we knew that other molecules relative to it were either similar or not. And so that's where the D and L system came from. In the 1950s, it turns out that there was a breakthrough in X-ray crystallography. Does anybody know anything about X-ray crystallography? There's one really famous example you should know something about, especially my biology friends. Yeah, that's right. The determination of the helical structure of DNA was done by X-ray crystallography. But until about the 1950s, you could tell whether or not things were this side of the molecule, that side of the molecule, but you couldn't really tell whether or not it was absolutely that way. You could just know relatively. But in the 1950s, they came up with an X-ray technique called anomalous dispersion that allowed them to determine whether or not something was in an absolute sense. And so all these D's and L's kind of went away, and now we have R's and S's, okay, except for the biochemists who held on to the D and L configuration. So today we can really pretty much determine the absolute configuration of almost any compound if we can get it to crystallize. Okay? That's kind of the key. All right, let's go back to how we're going to name these things. All right, so if 2 atoms on a stereogenic center are the same, things get kind of tricky. So for example, if we look at 2-butanol, yeah, that's 2-butanol, right? We know this is a chiral center because this is a methyl group and this is an ethyl group. That's a hydrogen and that's an oxygen of an alcohol. That's 4 different things. But lowest priority, top priority, how do I determine the priority of these 2? They're both carbon. So what do I do? I have to go out further and I have to look and see what it's bound to. That's exactly right. So we know that we have 4 different groups, carbon and carbon. So if we look at this, right, so we've got a carbon atom, we've got our hydrogen, we've got our OH, we've got a CH2 and a CH3, and we've got a CH3. So this is going to be priority 4, priority 1 because oxygen has a higher atomic number than carbon. I have to determine whether this is priority 2 or this one's priority 2. So we have to look and ask what's attached to these carbons that's not the chiral center. So what else is attached to this carbon? Just 3 hydrogens. So I go above this and I put 3 hydrogens in parentheses. Separate them by a comma. What's attached to this carbon? 2 hydrogens and a carbon. So a carbon and 2 hydrogens. I go in descending priority order within the parentheses. And then what you do is you look in the parentheses and you go until you find a difference. Can we identify a difference? Which one is going to take the priority? The one with carbon. Carbon outranks hydrogen every day, right? So this is going to be priority what? Again, lower number wins, right?
So it's still by atomic number?
It is by atomic number, but not of the atom directly attached to the chiral center because they're identical here. So you have to go out. And you have to continue to do that until you find a difference. Sometimes you have to go out several atoms, but rarely do you have to go out past 2 or 3. Okay? All right. So now we've got things prioritized. The next thing that you're going to want to do is build a model. And I know many of you are saying right now, I can do this in my head, and I've said this many times to you. You can't. All right? Build a model. It's very easy to get 2 things switched in your mind when you're thinking about 3-dimensional things. Okay? So always build the model. So here's our model of 2-butanol, where we have enantiomer A, which we're going to determine whether it's R or S in just a moment, and we have enantiomer B. Again, what does the solid dashed wedge mean? It's coming out of the plane of the screen towards us. What's the dashed wedge mean? It's going behind. And what about these groups? They're in the plane of the screen. That's exactly right. And so we can build a model. We can use 4 different colored spheres if we want. Assign them the priorities. And so here's what we know. We know that this is the priority order. OH is going to be number 1. The ethyl group is going to be priority 2, the methyl group priority 3, and a hydrogen is going to be the lowest priority. When you do this, I highly recommend that you, on your piece of paper, you write out the priorities on the atoms, on the groups, so you can see them. Okay? It's very useful to be able to do that. Okay? Now, what we have to do, and this is why building a model is so important, we're going to grab the lowest priority group, whatever it happens to be. In this case, it's hydrogen. And we're going to turn it away from us. Okay? So if we build a model, let's build a model of one of these enantiomers. So you need 1 carbon atom and get 4 spheres. White, green, blue, and red. Let's go back. And let's just build enantiomer A. So you've got a carbon atom, right? So if I imagine that being in the plane of the screen, like that may be hard for you to see, but this group that's coming out, there's my group that's going up. These 3 are going to be in the plane of the screen, right? These 3 right here. So this is going to be my OH. What atom or what color should I use for oxygen? Red, that's right. Kind of by definition. I told you the other day we typically use red for that. What are we going to use for carbon here? Pick one. Green. Okay, we're going to use green. So I'd highly recommend that we write that down, that green is carbon. Or the ethyl group. So we can keep track of it, right? Hydrogen is what color? We almost always use white, so that's going behind me, so that's going to be this one. I'm going to put the white one here. And so that only leaves blue left. So I'm going to put the blue one here, if I can get that on there. And so blue is equal to my methyl group. All right, so I have just built that model, right? There's the OH, there's the carbon, there's the ethyl group. All those are in the plane of the screen. Coming towards me is the methyl group, and going away from me is the hydrogen. No matter what I do in my mind right now, this will always be correct, unless I start breaking bonds, no matter how I turn it. If you rotate things in your mind in 3 dimensions, you will get things superimposed and translocated and all messed up. But this is your system to keep things in order. So we're going to determine whether enantiomer A is R or S. Okay? So what you do is you grab the lowest priority group. Grab it in your hand and turn it away from you to where you're looking down the carbon lowest priority group bond. That's what this little eye is showing us here, right? And in doing so, I see that I've got group number 1 going straight up, group number 2 going to the right, group number 3 kind of to the left side, right? Now, if I go priority group 1, 2, 3, as if I'm turning a car wheel to the right, it is which enantiomer? R or S? R. It is R, and that's easy to remember. I'm turning my wheel to the right, R, right? And so the opposite is S, right? Very, very important that we have the lowest priority group pointing away from us. Because if I look at it this way, how does it look like it's going? It looks like it's going the opposite. The example that I like to use for you all is time and clocks. Imagine you go to London and you stand out and you look at Big Ben. Which way are his hands moving? Clockwise, right? And time is as it should be. You're getting older, right? The day is getting longer and so on and so forth. If you take a tour inside Big Ben and you look outside at the face of the clock, which way does it look like time is going? It looks like it's going counterclockwise. Are you getting younger? Absolutely not. You're not in a time machine. You're looking at it wrong, right? The same thing goes here. If the lowest priority group is away from you, that is how we are supposed to be looking at this clock face, if you will. Okay? However, it is not always going to be that convenient for you, because I will not always draw them with the lowest priority group facing you or facing away from you. You will have to build a model, you will have to grab the lowest priority group, and you will have to turn it away. Okay? I'm not going to make your life that easy. Okay? It's because it's never that easy. Molecules have more than one chiral center. We can't draw them all going away from the plane, okay, to have the right relationship. So when the priorities go to the right, this is the R enantiomer. When they go to the left, this is the S enantiomer, okay? Just like that, just like turning a wheel on a car, okay? So we would call enantiomer A R-2-butanol. Notice that R is italicized and in parentheses, and it is separated by a hyphen between the two. That tells us how those atoms around that chiral center are located in 3 dimensions. Okay? I can go back and make that exact enantiomer and draw it out on paper and have the atoms in the right configuration. S would be exactly the opposite, S-2-butanol. Okay? So we have the R isomer, we have the S isomer. What do you know about the physical properties of enantiomers with respect to one another? Let's say S2-butanol and R2-butanol. What can you tell me about the, I don't know, let's say the boiling points? They are identical. R2-butanol has exactly the same boiling point as S2-butanol. How about the melting points? Same. How about the IR spectrum? The same. They have the same physical properties for the most part. You cannot really distinguish them very easily through techniques that you learn. Have you all done the TLC lab yet? Thin layer chromatography lab? You haven't done thin layer chromatography? Okay, well, we won't get into it. But anyway, they even have the same TLCs. They give you the same RF values for TLC, okay? And we'll talk a little bit more about that in a second. Here's another quick concept test for you. Using your same model kit piece that you've got together, figure out for me whether or not this molecule is R or S at the stereogenic center. Is it R or is it S? Think it's S? Let's see if we're right. So we're going to use the white sphere as our hydrogen. It's pointing out towards us. We're going to use green here for the methyl group, right? We've got the hydrogen. Let's see. So we've got the hydrogen coming out towards us. We've got the methyl group. We've got the isopropyl group, and we've got the oxygen. Okay, so that's going to be priority 1, priority 2, priority 3. So priority 1, priority 2, priority 3. If I look at it like this, it looks like it's going in the R direction, right? But I have to do what with this? I have to flip it, and so it's actually going in the S direction. So this actually has the S absolute stereochemistry at the chiral center, okay? This is an example of where the hydrogen is coming towards us, okay? Now, what if I had not shown the dashes and the wedges here, and I had just put a bond to hydrogen and a bond to OH? You wouldn't know, would you? You have to know whether or not something's coming out towards you or away from you. And in fact, if I didn't show you the dashes and the wedges, you would assume that it's racemic, meaning what? What does it mean to be racemic? No idea? What does it mean to be racemic? A racemic mixture is an equal mixture of both enantiomers. Okay? So you can have 50% R and 50% S in a mixture, and that is racemic. We talked about that the other day when we talked about the thalidomide situation, remember? Where they were giving pregnant women a racemic mixture of thalidomide. One enantiomer treated the morning sickness, the other enantiomer caused birth defects. Racemic, R-A-C-E-M-I-C, racemic. Equal parts. Now, there are some things that you're going to need to keep in mind when you're looking at carbon atoms that are attached to a chiral center. Okay? Just like when we looked at an ethyl versus a methyl group, right? It was carbon in both cases, and we had to go out and figure out what the difference was. Well, if the carbon atom is bound to a stereogenic center, is in this case, an aldehyde, right? That's a carbon atom, but it's a carbon atom that's bound to basically 2 oxygens, if you want to think of it that way. It's just the same oxygen. It's got 2 bonds to oxygen. That's equivalent to a tetrahedral carbon atom that looks like this with 2 oxygens and a hydrogen attached to it. So that's what you would put in parentheses. You would put oxygen, comma, oxygen, comma, hydrogen. Okay? And you would try to figure out there. If your carbon atom is a carbon-carbon double bond, part of an alkene, that is equivalent to a carbon that is bound to 2 other carbons. Okay, so you would put those in there. If it's a carbon-carbon triple bond, that would be the equivalent of a carbon atom bound to 3 other carbons. Okay, so you have to think about that as you are assigning priorities. It's really great if the atoms are different around the chiral carbon. Then you just look at atomic number. What would it be if we were looking at, let's say, a chiral center that had a deuterium, a tritium, and a hydrogen, and then say some other carbon atom attached to it? How would we determine priorities there? Tritium, deuterium, and hydrogen are all isotopes of hydrogen, right? Right? Tritium is heavy hydrogen. Deuterium is heavy hydrogen. Tritium is radioactive, right? So how do we determine priority there? Because they all have the same atomic number. You go by mass, right? So deuterium has a higher priority than hydrogen, and tritium has a higher priority than deuterium, okay? So when you're looking at isotopes, you have to look at the mass, and it matters, okay? It does matter. Let's look at something you might be a little more familiar with, Ritalin. And let's look at the single chiral center that I have identified there. There's another chiral center in Ritalin, but I don't want you to worry about that one yet. Okay? Tell me whether or not Ritalin has the R or S configuration at that chiral carbon. That's a bad ring. How do we assign the priorities? What can we assign right off the bat? Hydrogen. That's going to be 4, right? And guess what? I turned that one away from us, so that makes life easy, right? So now I've got carbon, carbon, and carbon. Can I make a decision? Absolutely not. So I have to ask myself what's attached to these carbons. What's attached to this carbon? 3 oxygens. 1, 2, 3. Right? What's attached to this one? Okay, so in this one, let's see, I'm going to just put it out here. I have what? Nitrogen, carbon, and hydrogen. We're going to do it in descending atomic number, right? And what about this one? Carbon, carbon, and carbon. So all carbons. So can I make a decision? Which one takes priority? Oxygen is higher priority than nitrogen and carbon, right? So we can make a decision here. So that's going to be priority what? It's going to be number 1. Now what about here? So it looks like it's going what way? It is going S. Okay. Where's the other chiral center in Ritalin that I didn't show you the stereochemistry for? One attached to the nitrogen right there. There's a hydrogen, nitrogen, carbon, and a different carbon group. Ritalin actually has 2 chiral centers. Okay? But we're only looking at this one particular chiral center. Now what you're going to find in nature is that a lot of molecules that we find useful in biology actually have the S absolute stereochemistry. And those actually are the same thing as the L in the D and L configuration for the most part. Okay, so L amino acids have the S configuration for the most part. Okay? And I wish I had a grand story to tell you about why nature selected S. I don't actually know that. It's a philosophical question that people are still pondering. But it does seem to be the case that in most cases the S enantiomer is selected for biological activity. Okay? Now we've already talked about this a little bit. If we have an equal amount of 2 enantiomers, we're going to call that a racemic mixture. Some people call that a racemate. I just say racemic mixture. Or I say that it's racemic. I rarely use the term racemate, but just my preference, okay? Now, we just mentioned that the melting point are going to be identical. So if we have the R enantiomer of a molecule and the S enantiomer, and we try to find their melting points, we're going to find that they're identical. We're going to find that their boiling points are going to be identical. We're going to find that the enantiomers by themselves with respect to the racemate may or may not have the same physical properties. Okay, so for example, I can take the melting point of leucine, that amino acid that we talked about before, the R enantiomer of it, and I can take the melting point of the S enantiomer of it, and I find that they're identical. When I mix the R and the S together, actually the melting point is lower. Okay? It matters. Okay, so The racemic compound quite frequently has different physical properties from the the enantiomers isolated on their own. However, when we look at optical rotation or optical activity, we're going to talk a little bit more about that in a moment, the enantiomers will rotate plane polarized light in opposite directions but of equal magnitude in terms of the degrees of rotation that you see. So if the R enantiomer rotates the plane polarized light, let's say in a clockwise fashion for a particular molecule, the S enantiomer will rotate it in exactly the opposite direction. A racemic mixture, however, will not rotate plane polarized light at all. Can anybody tell me why that might be the case? Pardon? They cancel out. So for all those molecules that are rotating plane polarized light to the left, you've got an equal number that are rotating them to the right, and they cancel out and you get 0 degrees of rotation, okay? So it turns out that optical rotation is one of the few things that we can actually use to distinguish one enantiomer from another. I have a machine down in my lab called a polarimeter. It's about $16,000 that determines whether or not light is being rotated in one direction or the other. It's a very precise instrument that allows me to get down to very small degrees of rotation very accurately. These different enantiomers have pretty interesting properties other than just being able to rotate plane polarized light in opposite directions. For example, if you take the molecule carvone, which has a chiral center shown here and here, if you have the R enantiomer of carvone, it smells like spearmint. It's what the spearmint plant produces. It produces R carvone. However, caraway seeds produce exactly the opposite enantiomer. Have you ever smelled caraway and spearmint? Do they smell the same? They have different odors. They have very distinct and different odors. Okay? I prefer spearmint to caraway. Okay? If you ever cooked, you'll know. Okay? So why would we have different smells for these things? They have the same melting points. They have the same boiling points. They have the same IR spectra. What's different? They do have some different properties, but the property that we talked about was just rotating plane polarized light. Does odor have anything to do with light? No.
The way they bind to olfactory receptors.
That's right. It's how they bind to your olfactory receptors. They bind differently. Okay? If you think about R carvone as being a right-handed glove and S carvone as being a left-handed glove, okay? And you have your right hand, does your hand fit into both gloves the same? Not at all. And in fact, the receptors in your nose are chiral. They're one hand. So if I take the right hand and the right-handed glove, that fits better than the right hand and the left-handed glove, right? And it gives rise to a different signal in the brain, okay? So how these chiral molecules interact with other chiral materials can give rise to different chemical things, okay? And that's very important, okay? Some other things that you need to keep in mind. Our medicines that we take are quite frequently chiral. Everybody complains about the cost of their medicine, right? It's expensive. Part of the reason why is because we're making more and more complex medicines with more and more chiral centers, and if you have the wrong chiral center, maybe it does no harm, maybe it kills you. Okay? And you got to have a chemist, not just a chemist, you got to have lots of chemists that sit there and figure out ways to make the correct enantiomer. So for example, ibuprofen. What's the trade name for ibuprofen? Anybody know the brand name? Acetaminophen's Tylenol. Advil, right? So if you take Advil, that's ibuprofen. Okay? The S enantiomer of ibuprofen is actually what is responsible for the anti-inflammatory properties of ibuprofen. Okay, so if you know somebody that has a little arthritis, they may take ibuprofen. It's the S enantiomer of ibuprofen that is responsible for that. Go home and look on your ibuprofen bottle and see if it says S ibuprofen. It does not, meaning that they're selling it to you how? As a racemic mixture. Okay, so that 1,000 milligram, or well, you probably not take 1,000 milligrams. Let's say you're taking a 100 milligram tablet. Only 50 milligrams of that tablet are actually doing the job. The other 50 milligrams are just being processed and excreted by your body harmlessly. Okay? However, that's not the case for Aleve. Naproxen sodium. When you go buy naproxen sodium, it will tell you that it is S-naproxen. And it better be 100% S-naproxen. Because S-naproxen is the anti-inflammatory agent, but R-naproxen kills your liver. Switching these two groups, their space in 3 dimensions, will kill your liver. And it's a very potent liver toxin. Like if you took a couple of pills of R-naproxen, it's pretty much so unrecoverable. So, do you depend on chemists to know exactly what they're making? Absolutely. And the Food and Drug Administration has come out with rules over the last several decades where pharmaceutical companies have to prove that if they're selling something as a racemic, that both enantiomers, they have to identify which enantiomer does the work, okay? And they have to prove that the other enantiomer causes no harm. How easy is that to prove? It's essentially impossible to prove for the most part. It's hard to prove that something causes no harm. So what are pharmaceutical companies doing? They put a lot of warnings, but they also spend a lot of money making only the enantiomer that they know gives you the benefit. Okay? Does anybody know how much it approximately costs to market a single drug these days, to get it from idea to bottle on the shelf at your pharmacist? Huh? A minimum of $1 billion. Every new drug, for the most part, that's coming out on the market today costs at a minimum of $1 billion to get it to your pharmacist's shelf. That's a lot of cash. And they have to reap that cash back because they're for-profit companies, right? And they have a patent that runs out. Patents run out in 20 years, right? So depending on when they patented it. So it doesn't take long to figure out why your drugs cost so much. They're expensive, okay? Let's look at another example. This is a structure of methamphetamine, okay? Anybody know who that guy is? Walter White, right? He's one of my heroes from Breaking Bad, okay? He's a villain, but he's a great villain, I think, okay? So, chemistry teacher gone bad, right? He made methamphetamine, which, by the way, is not blue. That's a myth, okay? I don't know why they did that in the show. But anyway, he made this high-quality methamphetamine, okay? Now, it turns out that just about everybody in this room, whether you know it or not, you have probably taken a small amount of methamphetamine. But that does not mean that you're a meth addict, okay? There are medical reasons to take methamphetamine. So, for example, the stuff that gives you the high that's no good for you is actually S-methamphetamine. The S enantiomer, gives you that euphoric stuff. The R enantiomer, however, is commercially available in Vicks Vapo inhalers that you can go down and buy right now. You do love those? It's not because of the meth, because the methamphetamine causes no high if it is the R enantiomer. Okay? But what it does is it opens up your airways, okay, and allows you to breathe easier. And so there's about, I think it's 20 to 50 milligrams, something like that, of R-methamphetamine. And in fact, they call it Lev methamphetamine. Go look at one of the packages in the drugstore. It'll say contains Lev methamphetamine. Okay? They all have this same connectivity. It's just the difference. Okay? The stuff that's actually stolen on the street for illicit purposes is not pure S-methamphetamine. It's a racemic mixture. So only half of what you're buying on the street causes the effect. The other one opens your airways an awful lot. Okay? But one of the things that they didn't mention in Breaking Bad was that the process that Walter White went through produced only the S enantiomer. And that's why his stuff was so famous. Okay? It was very potent because on a per gram basis, it was all giving them the high, right? And so that's how he became famous doing this. Okay? So these are enantiomers of one another. Legal to buy, legal to own. You can carry this in your car, no problem. Have this with you, you're in trouble, right? All right, so I tell you what, let's stop there for today. I got to hand back some stuff. I want you all to read before we get into class on Wednesday about optical activity. We'll finish this up before we do the inverted lecture, and I've got actually a demo that I want to show you about optical activity. So we'll read on that.